My talk is titled Engineering Lessons Learned by Data Scientists in Growing MalwareScore from Kaggle Competition to Trusted Antivirus Solution. So that's a long title, and I guess I'm going to get right into that type of thing. But probably what I could have titled this talk is Where We Screwed Up. And there were a lot of places where we did screw up, and hopefully we've learned a lot of lessons that we can then tell you. So yeah, this is kind of some background about me. I got my PhD in physics working for IceCube. I got to go to the South Pole. That was pretty awesome. But I eventually ended up as a data scientist here at Endgame, a cybersecurity company. And in putting together this slide, I kind of thought that my data sources might be getting a little less cool as time goes by. But I mean, I probably won't be able to beat photomultiplier tubes at the South Pole ever. But that's all right. Yeah, so like I said, this talk is going to be a little bit kind of like a story time. I'm a little uncomfortable with that because I like to present results or open source a tool or something. But this is going to be a bit more high level and just kind of what happened as our team tried to develop this product that we eventually called MalwareScore. And kind of the main thread going through the whole story is going to be how our small team of data scientists kind of balanced the speed of development and the maintainability of the things that we were producing. A lot of the times we kind of went too far on one of the sides, but that's all right. We learned our lessons and we kind of regrouped at each of those times and went forward. So first, before I start, I'm going to give you a little advertisement. Sorry about this, but I feel like at conferences like this, data science and security, you don't really see it so much. So let me talk to you about why I like it. And kind of didn't really expect to like it when I joined a security firm five years ago. But the benefits as I see them is the mission. I kind of really believe that consumers' privacy needs to be protected, and that cyber attacks from other nations really need to stop. And I really enjoy contributing to a firm that's trying to build towards that mission. Also, it's a very relevant field. You're always going to see companies making the headlines by making mistakes in this sort of in cybersecurity, and so you feel like you're always going to be working on something that's pretty important, and also opportunity. This kind of deep learning architecture that's very complicated and has produced great results in the field of images. Well, that really doesn't exist in security right now. I feel like there's not as much manpower, there's not as much funding behind creating the really latest, greatest, coolest thing. And so there is an opportunity to come up with the next cool thing in cybersecurity. Just to give you a quick overview of the type of products that are possible by being in data science and security. Here's kind of a list of them. I'm not going to go through all of them, but I'll just highlight that what we're going to be talking about for the next 20 minutes or so is malicious file classification. That's kind of the problem that I at Endgame chose to tackle. All right, so enough of that ad. So 3 years ago, this MalwareScore thing kind of started with this Kaggle competition here. Microsoft released a bunch of malware samples in 10 different malware families, and they open sourced that data on a Kaggle as a data science competition. And they asked you to classify each new malware sample into one of those 10 families. And so I was a data scientist at Endgame at the time. We were researching new products, new ways to apply data science in security. And so I thought I should really jump into this. I should know what's going on in my field. And so I participated. I saw all the cool things that all the other competitors were doing. I mostly used it as kind of a learning platform because for me, Kaggle is definitely best as a place to go to learn all kinds of techniques. The best competitors on that website definitely are really great at wringing the last few drops out of every data set that is up there. But that's not always the best skill for productionizing something. But what I do like Kaggle for is the ability to learn. But anyway, I competed. I got 27th out of 500 people. I thought I should maybe do better since I was just surrounded by so many cybersecurity experts at Endgame who were always willing to answer my questions about what a PE file is, what a Windows executable is, what the different parts of it are. But through all the competitors at Kaggle and all my coworkers, I was able to learn a lot. And yeah, the thing that kind of grew out of it then after the competition wrapped up was MalwareScore. Was, okay, what lessons can I learn from this competition and how can I convert it into a product? And so the problem that we wanted to solve was not just taking a piece of malware and applying a family label to it, but it was, let's solve the whole antivirus problem, because that's what we're going to be able to productionize and that's what we're going to be able to sell. So that's kind of the direction we went to after learning a bunch of background information from the competition. And yeah, so we started work on MalwareScore. I'll give some background information about it first before kind of diving into how we developed it. But it's a machine learning first antivirus solution. Our solution is lightweight, it has static features, a fast prediction time, and it's deployed to customer machines. And that's kind of the element that makes all these other things important. Like we need to be lightweight, because when we release a model, we need to distribute it to all of the customer workstations at a company. And we need fast prediction times, because when somebody double clicks on an executable, we need to evaluate all those features, we need to calculate them, and we need to evaluate the model immediately. We don't want to add too much latency to someone using their computer, because then users are just going to get frustrated and they're going to not like your product anymore. And the one other factor is that we want, because we want that kind of speed, we want those decisions to be like on the workstation itself, and we don't want them to call out to a customer appliance or the cloud or any of our own servers to help make that decision. We want that decision to be made on the customer workstation and very quickly. Yeah, so we developed it. VirusTotal is a website that kind of brings together all the different antivirus engine decisions. It's virustotal.com. You could go there right now and upload any Windows executable that you're running, and VirusTotal will take that file and return to you all the answers from all different antivirus engines about whether they think it's malicious or benign. So it's kind of cool to have the engine, the model that I built, kind of deployed up there to be judged by everybody else, but it's also a little bit stressful. It leads to definitely our successes and failures being called out, on a daily or weekly basis. It adds pressure, and it forces us to be on the top of our game. Yeah, so let me talk a little bit about the features that we developed. I don't want to get into the features that are in MalwareScore itself, but we did open source a data set that contains a simplified version of our MalwareScore features. It's called Ember, and it's available at our company GitHub right there. And so for Ember, we released these kind of features from a large set of Windows executables. We couldn't release the executables themselves because we don't have those intellectual property rights, but we could calculate simplified features and then release those to the wider community. And those features that we decided on were first, the ones in the first column, like byte histogram, byte entropy histogram, and strings. Those can be calculated just from the raw bytes of the file. You don't really need to understand the file format itself to be able to get those. But then, there are also a lot of specialized features like section information, general, what's in the header of the PE file. And all of this type of stuff requires you to have a parser that understands what a Windows executable file looks like on the inside and where the data is. And yeah, so yeah, this is all those features. I have some examples here. This is all straight from the Ember data set that you can download. But this is kind of what the section information looks like. Each Windows executable file has lots of different sections with different information in it, and there's definitely a header with lots of information that you can grab there. All right, so those are the features. The model that we decided on, we went with gradient boosted decision trees, and on Endgame's technical blog, we have a blog post that kind of runs through all of our thinking and why we chose gradient boosted decision trees. We wanted to balance a bunch of different things like accuracy, prediction time, cost to retrain, and the size of the model. And you can go onto that blog and kind of see how we balanced those, what other models we tried out, and where they where they had strengths and where they had weaknesses. And we found that gradient boosted decision trees just had a great accuracy with prediction time and the size, a small prediction time and a small size of the model that really allowed us to deploy to customer workstations. So I was kind of describing the whole product there to kind of give you some background information. But now let's go back to the beginning after that Kaggle competition and talk about how we started off. And this is kind of how we started off. One of the data scientists on our team had some previous experience in Mongo and kind of just spun one up on our local development machine. And then we kind of all individually went on and tried to develop features for our MalwareScore model. And kind of the Mongo setup of having a database and then separate collections. We had different separate collections for each feature that we were investigating. And that kind of allowed us all to develop independently and then fill up the database with features calculated from our kind of small training set at the time. And this really let us go pretty quickly. So when we wanted to actually train a model on these features, it was kind of awkward at that time because we needed to get all the data out of MongoDB. And not only that, but the main method that we knew about to getting all the features out of MongoDB was this find, searching over the hash for each sample. And so we had to loop over groups of samples and then loop over the features that we were interested in, and then find all of those features for each sample and line them all up in a large matrix. And this was definitely awkward, but it definitely worked for a while, at least, until our data scaled out and until to become too large for this to started taking days at a time. At that point, our development was to a point where we had decided that what the features were going to be, and we could calculate those and just keep them in one collection. We had kind of frozen the features. And so at that point, we could move to kind of a better solution, which is the parallel scan, where we could just grab all the features out of just one single collection. But again, I don't believe MongoDB was set up for that kind of thing. That's not the operation that the creators really envisioned. And so also, as the data set grew, this solution fell over as well. And so, yeah, the lesson here that I think we learned was not to rely on the proof of concept framework for too long. I think MongoDB really worked for us when we could start experimenting. But then when we made the decision, like, yeah, this is a viable product, we want to go through with this, I think that was definitely the time for us to kind of step back and rethink what we were doing. Our solution eventually, when the MongoDB eventually fell over, or we just got impatient and we didn't want to wait days in order to get our features ready for training, was we went to MooreaDB. Once they were frozen, we were able to put all the features into just one table. And also by this time, we kind of were advanced in how we were going to label each of the samples that we had. We knew what criteria we wanted to use for benign and malicious. And so we filled all kinds of tables with lots of metadata about each of our samples. And at this point, we were able to say, this is the SQL query that defines what's benign, and whatever we get out of this, that's going to be our benign side. And then here's the SQL query that defines malicious. And the cool thing about having just one query for that is we're able to track that over time and see what we've changed. I hinted at it about a slide or two ago, but let me just give you this talk recommendation. I really enjoyed this talk. This is Designed for Continuous Experimentation by Dan McKinley. And I'm going to read off the slide here. But Dan says to experiment early and often on new designs, products, and abandon those that don't add value. And I think that's what we did really well in the early days. But we were kind of experimenting and seeing if this MalwareScore was going to work. And we did, but then my corollary is that when the product worked and when we decided to go forward with it, that was kind of the moment when we should step back and say, all right, how should we architect this? As our data set grows, what problems are we going to encounter? I really think that's what we should have done. All right, so that's one lesson. Let's move on after that. So as the data size grew, we had been training just on one single machine that we kind of had left over from a previous product. that Endgame had discontinued. And that was working well for us, but again, as our data size grew, we couldn't train on that one machine anymore. But we were learning tricks like to kind of extend the lifetime of how long this server was going to able to train our model. Through experimentation, we found that we could mem-map the features from disk and then load them into the XGBoost internal data representation, right from disk. How we had been going up to that point was we'd been reading the features in NumPy, in memory, and then converting them over to the XGBoost data representation. So we'd have the features in memory twice, and that was really the limiting factor that made it impossible to continue training on that machine. But through this trick, we were able to kind of, extend the lifetime of that machine, double it, just because we only needed the features to be in memory just once. And yeah, that's kind of some pseudocode. That's kind of some simplified example of our training code there of how we did that. So again, eventually we grew out of that server. We knew we had to go distributed. We knew we had to train this machine, this XGBoost model in a distributed way. But I kind of think we were kind of still really kind of too focused on cost. We wanted to see, how cheaply we could train this model in AWS is where we were. And so we kind of took this memory mapping solution and hacked ourselves onto a Dask setup and started implementing it that way. So we have our features in S3. We would read them over to our EC2 nodes that we'd spun up and write those features to the hard drive, the elastic block storage that we had attached to each of those EC2 nodes. And then we could memory map from that storage into the EC2 node's RAM. And in this way, again, we wouldn't use the EC2 node's RAM twice. We would have the features only in the RAM once. And that way we could train on less nodes total. Of course, this kind of fell over at one point. Like I said, we had hacked kind of one framework. That framework was Dask to do our bidding. This wasn't kind of an approved, released method of reading data in. And at some point, some of the package dependencies, they were creeping forward. There were new versions were being released that we weren't freezing. And at one point, we just couldn't train models anymore. And that was a fire that needed to be put out with lots of panic. So my lesson that I kind of took away from this whole experience was not to focus on small cost savings early. At one point, it made sense for us to continue trying to train on just one server, but we really shouldn't have been focused on bringing that kind of method when we went distributed. So yeah, we were able to work through it. We were able to dig through the package dependencies and freeze everything. But once again, that's kind of, once we've frozen all those versions, we can't really move forward. And we are kind of at a spot now where we're training with older versions of this software. And we do need to decide and move forward with a new framework. All right, so that's the second lesson. Let's move on here. So yeah, deploying the model and making predictions on customer workstations requires safe, robust code that is also very fast. I've talked about that. I've talked about how we've made predictions kind of autonomously on customer workstations without calling out to anything else. And not only that, but I'd also want to kind of stress the safety required. We have a sensor development team. That's what we call our software that runs on customer workstations. We call it the sensor. And those developers are really great at just being very safe. If we ever crash or blue screen the box, that's going to lose a lot of trust in the customer's eyes. And so our developers are really careful to not make that a possibility. But that's kind of tough because all those sensor developers, they're experts at coding in C and C++ and coding in Windows, something that I'm not an expert in. But then they are also not an expert in these machine learning models and how to write code to evaluate them. And so we needed to meet up and kind of meet in the middle. And so the method we did for that was I kind of wrote some bad code, some C, some proof of concept code that evaluates a model and then wrote many tests around it. So here's a bunch of features. Here are the predictions that we expect by running this code. And here's the code to do it, and we handed it over. And again, this took me a long time to kind of get trained up in the sensor team's development boxes and their environment. And I never really totally got there, but I was able to, go far enough that I was able to hand it over to them to, this code that passed a couple tests, and then they were able to take it from there and really make it safe and reliable, and so that it can run on customer boxes. Yeah, so what I kind of want to stress here is so this lesson is actually one that we did right and that we didn't fail at. But I think we were very good at defining a well-defined interface between data science and the engineering, where I could train the models, our team could train models, and then hand over something in a data structure that the engineers definitely expected and knew how to work with. So this is kind of our deployment process now, just kind of an overview, a schema of it. We train the models, we transform that model into our own internal data structure, store that in kind of a binary store, and then the engineering team is able to take care of deploying that to all kinds of customer appliances, who then distribute that model to all kinds of customer workstations. And there's a bunch of tests run in Jenkins that also depend on all those artifacts that we ship to our binary store. So yeah, the lesson there is that it's very advantageous to define a format for smooth handoffs between engineering and data science. And once you get to that interface, it's really going to help you. All right, so I think this is the last lesson. I'm going to talk a little bit about how we evaluate each model. And we use a tool, an internal tool called Bit Inspector. And this is really just a web front end that kind of communicates to managers how the training process is going. We also use it to solicit feedback from all kinds of domain experts. We have a lot of great reverse engineers, people who are experienced with what benign and malicious software looks like. And so we kind of give those kind of experts all the scores and all of our models and tell them to find errors and label samples that we might be getting wrong. And then we take all those labels and use them in future training. Yeah, so it's built with Flask and a bunch of visualization tools. One of the advantages of doing this was, the code of Bit Inspector kind of connects to all kinds of data sources in Endgame, and it kind of became a way to communicate to new data scientists, to people joining the team, exactly how they could connect to those resources. If someone was asking, like, how do I go grab a sample if I have the hash? And I was able to point them to code in Bit Inspector that did exactly that. And there were a lot of examples of that. It was one of the unexpected benefits of building this internal tool. Maybe that points to a failure of documentation instead of, but I'll rack it up as a benefit. This is an example of some screenshots of this kind of web front end. It's a front end that only a data scientist can love. You got the hash of the sample. So this page here shows like one sample, and then it shows a bunch of the last few models that we trained. It shows the score of that on that sample, back in time. So this kind of gives us a really good resource, because we can, if something new comes out, we can say, oh yeah, we got that right. This is malicious. We would have blocked it. And not only that, we can say, oh, we would have blocked it as of January last year or something like that. So that's kind of a cool tool that allows us to communicate that to customers. And then I also threw on some visualizations of some of the features. That's the byte histogram up at the top. And then here is the byte entropy histogram. The entropy is on the y-axis. And you can see like packed software that has high entropy. That kind of shows, that software kind of shows up with blue boxes at the top. So it doesn't immediately show you kind of what the software is, but after looking at a couple of these over time, you can start to see patterns and start to learn about what the software is. Also on the model page, we have, so yeah, there's two different interfaces. You can upload a sample, and then it'll tell you all about the sample, and then you can click on just one model that might, the most recent one that might have been trained, and then you can see all kinds of metrics about how well that model's performing. And you can see receiver operator characteristic curves and area under those curves. And then also distributions of the scores on all of our training set, and some confusion matrices. And not only that, we don't show that for only just all the data. The cool thing is we kind of split out the data into different subgroups. For example, we had trouble a while ago with just benign installers, and the model wasn't performing very well. And so what we were able to do is tag all of those benign installers and give them that tag, and then kind of break them out, and so that we could track the distribution of scores on that one subgroup of files and make sure that not only did we fix the issue, but we're continuing to keep that issue fixed over time. So yeah, Bit Inspector was awesome for tracking the efficacy of all the models we built. It gave us a lot of confidence to release a new model every time we trained a new one, but it wasn't showing us the data ingest. It wasn't showing us kind of the health of our databases and everything like that. So at some point we ran into a data ingest problem where we kind of missed data over 3 weeks. And that was a problem. Luckily, the APIs we used to get data allowed us to kind of replay. We were able to go back and at least get a fraction of the data that we were very interested in. And so the lesson I took from this is kind of summed up by this meme here. A system built by data scientists, we're going to be very worried about our model and how well it's performing, and we kind of ignored the thing that model is built on, which is the data ingest. And so, yeah, efficacy checks on the pipeline as well as the model are very important. So that's it. That's all my lessons. All 4 of them are summarized here. So thanks a lot for your attention.
Can you talk more about the unit tests that you were using to enter code off your engineering team?
Sure. So I mean, there's a bunch of tests. The main one I had in mind when I displayed that was we have a canonical set of samples, and we know what the feature calculation should be, and that that shouldn't change no matter what the model is, really. So every time. Actually, that's a daily regression test on the sensor code itself. We want to make sure that the feature calculation never changes. So that actually just runs overnight. I guess, yeah, so there's a bunch of other tests that involve the model. Every time I train a model, that canonical set of samples, I also score them with a new model and then upload those scores to that artifactory. And so those regression tests then also match the features to what we expect, but then they also match the scores. There's a lot of other tests too, but yeah.
That's the big the regression code, right?
Yes. Yeah.
You talked about the problem that you had with the data ingestion. I'm still curious, how do you usually collect data? What is your data sources? What are the data sources?
There's a variety of data sources, like from our customers, from different partners. We pay for data from different companies. And our data ingest has kind of changed over time from just a kind of Python script that runs and hits those APIs from those people we buy data from, to now we kind of have a more sophisticated setup of daemons that run in the background and that are being monitored. But yeah, I didn't want to talk too much more about the data ingest unless you had a specific question about that.
I have a question. I saw some tweets that you didn't read, but they seemed pretty positive.
Yeah, one's positive, one's negative.
Saying that you caused something everyone else did.
Yes.
Can you talk a little bit about the benefits of your approach?
Yeah. I mean, there's a lot of people in this space. We have internal metrics that make us think that we're doing really well, the best. Yeah, I just think we've approached the problem. We used to position our product as we use machine learning and nobody else does, and that was kind of a naive place to come from. All these other companies are using machine learning, but I think they're attaching it to kind of old legacy engineering structure, and so they find it hard to get it in. And so I'm kind of borrowing the mobile first catchphrase from years ago when new companies would want to develop for mobile first. We want to develop this antivirus solution for machine learning first and then clean up the details later. And I think that's the right approach now, and it's an approach we can take because we're kind of new.
So this works really well for malware. Are you doing something similar on the behavioral side? So effectively for the intrusion detection, et cetera?
We're doing research to that, definitely. But that brings up all kinds of complications as far as data collection. You need sandboxes, you need to instrument everything and record everything. And there's definitely challenges in when do you, if you see behavior coming across on a workstation, when do you evaluate a model? Like, when do you flag when that behavior is bad? We're looking into all of that. I expect we will come up with something, but it's definitely still just research right now.